Welcome to Lecture 7.3, the heat and wave equations in higher dimensions. There are three fundamental PDEs in Rn that we've seen. There's Laplace's equation, which is Laplacian of u equals 0. There's the heat equation, which is ut equals c squared Laplacian u, and the wave equation, which is utt equals c squared Laplacian u. In this lecture, we will solve the heat and the wave equation subject to various boundary conditions. Now, you can certainly have different boundary conditions, Dirichlet, Neumann, mixed, etc., on both the heat and the wave equation, and also homogeneous and inhomogeneous boundary conditions on these. But I'm going to argue that at least when you're starting out, it's more natural to have these unusual boundary conditions on the heat equation than the wave equation. For example, if you have a square region, maybe this represents the temperature in a room. Maybe you're looking at it top view, or almost top view. So this is X and this is Y. Then it's natural to think about maybe a few heaters. Maybe there's a heater along one side of the room, or there's a window on the other side. This is a situation when you have inhomogeneous boundary conditions. You can also have non-Dirichlet conditions. If this is completely insulated, then you have Neumann boundary conditions. Now, for the wave equation, you can certainly impose inhomogeneous boundary conditions. That would happen if this drum or this vibrating membrane did not have a flat boundary. For example, if you take that coat hanger example that we saw in the previous couple lectures, I forget how, earlier in a recent lecture, and we try to make a drum out of this and this thing were vibrating, yeah, then this would certainly be the wave equation with inhomogeneous boundary conditions, but I would say this is less natural physically, at least starting off. Maybe in nanotechnology or biology or advanced material research, maybe this is more natural. I don't know that. But at least in an undergraduate class, in my mind, when I'm thinking about modeling, inhomogeneous boundary conditions are more natural on the heat equation. And similarly, Neumann boundary conditions are more natural as well, because that corresponds to insulation. What does it mean if we have Neumann boundary conditions on the wave equation and the rate of change is not passing through the boundary? Well, for most things like a vibrating membrane or a vibrating string, the boundary is fixed. That's a very natural interpretation of Dirichlet conditions. Okay, now if you want to, you can Google Neumann boundary conditions, wave equation. You'll get a ton of results. So I don't want to say that these don't exist or it's not possible. I'm just going to say that at least in an undergraduate class, I think it's more natural to have homogeneous Dirichlet conditions for the wave equation. We will solve the heat equation first. So to solve a boundary and initial value problem for the heat equation in 2 dimensions, that's just ut equals c squared uxx plus uyy, we take the following steps. First, we will find the steady state solution. So this happens when ut is equal to 0. So to do that, we have to solve Laplace's equation with the same boundary conditions. Now, if your boundary conditions are 0, whether they're Dirichlet or Neumann, this is really easy. Just 0 is the solution. So just think about the heat equation on a square region where the endpoints are fixed at 0. You don't even need to do that step here. So this amounts to finding a particular solution. Think about when we solved the ODEs. If the equation is homogeneous, sure, 0 is a particular solution, but you don't think that way. You just skip the step and solve it. And the second step, or the first step if you just skip this one, is solve the related heat equation with homogeneous boundary conditions. Then we add these two functions together to get the final solution. That's u of x, y, t equals the steady state solution of x and y, and the solution to the related equation with homogeneous boundary conditions. Here's a picture of this. Let's suppose that we want to solve the heat equation on a square region with inhomogeneous boundary conditions. So here's a picture of that. This is the same thing that we saw when we studied Laplace's equation. And let's suppose that the initial condition here is something wild and crazy. So it's something like this big surface. Now, what's going to happen over time? So over time, heat's going to dissipate. This thing will flatten out. And what we will get is the steady state solution, which is the harmonic function on this boundary. So let me try to sketch that. So it's this soap bubble solution. That's how I like to think of it anyways. So this is the steady state solution. It's not changing over time. It's fixed. What we want to find is we want to find the solution to the heat equation. So this blue curve maybe is the initial condition, u of x, y, 0. And then over time, this is going to die out. So what we have to do is we have to solve the related equation. So instead of solving with these boundary conditions, solve it with 0 boundary conditions. Now let's see if I can actually sketch this. So with the same initial, almost the same initial condition. You take the initial condition and you subtract off the steady state solution. And I'm going to call this UH of x, y, t. So to find this solution, you have to find the steady state solution, and then you got to solve this. And that's what we're going to do today. Our first example is solving the following initial and boundary value problem. Sometimes we write this as B/IVP for short, for the two-dimensional heat equation. So the boundary conditions are all going to be 0, Dirichlet, and then we have this initial condition right here. So let me try to sketch this. So this is a square region, and x goes in that direction, say, and y goes in that direction. So this is 0, 0, and this is pi, pi. I'm going to do what we've done in the previous few lectures. We've spent enough time in Fourier Series dealing with arbitrary lengths, L, and you get this n pi x over L instead of just nx. And it makes things messier, but you can deal with it in the 1D case. And in the 2D case, I want to simplify things. It's going to be messy enough so you can really see what's important and not get cluttered with these pi over L's all over the place. Okay, so the temperature along this region, or along the boundary, is fixed at 0. And then we have this initial condition. I'll try to draw it, but it's going to be very wavy, and then it's going to be negative for part of this as well. And then as time goes on, this thing is going to just flatten out and approach a steady state solution of 0. Okay, let's solve this. So we're going to use the same method that we use for all of these, separation of variables. We will assume that u of x, y, t is that there is a function, or there is a solution of the form f of x, y times g of t. In other words, a function of position times a function of time. And we're going to plug these things back in. So let's take derivatives. So ut is equal to f times g prime. And, well, this I'm going to write as c squared times the Laplacian of u. So the Laplacian of u, this is the Laplacian of f times g. If you don't like that as much, then notice this is just f x x g plus f y y times g. So you factor out a g and you get the Laplacian of f times g. Okay, let's use these 0 boundary conditions now. So let's write the 0 boundary conditions. So the first one is u of 0 y t is f of 0 y times g of t, and that equals 0. Well, what can we conclude? Well, this is a non-zero function of time, and we're multiplying it by this. This is a function of y, but this could be 0. Like if the function were like x times y, and we plug in x equals 0, then we will get 0. So this can be 0, and it has to be 0 because the product is 0. So we get right away that f of 0 y equals 0. Now we have 3 more of these. I'm not going to do all of them out, so I'm just going to say 3 more boundary conditions lead us to conclude that f of pi y and f of x0 and, oops, I didn't mean to, and f of x pi are all equal to 0. So these are our boundary conditions for f. Okay, now let's actually plug this back into the PDE right here. So plug back in, and if we do that, we get that ut is f g prime equals c squared Laplacian of u, which is Laplacian of f times g. Now we'll do what we always do when we have an f and a g here, is divide through by c squared fg. C squared fg. And when you do that, the left-hand side, well, the f's cancel, and the right-hand sides, the g's cancel, and the c squareds cancel. Now don't cancel the f's here, because Laplacian of f, you can't separate that. Okay, so this, you get g prime over c squared g equals Laplacian of f over f. This thing on the left, this is a function of time. It does not depend on position at all. And it's equal to this quantity, which depends on function of position. This does not depend on time. So whatever this is, it has to be independent of position and time. It has to be a constant. We'll call it negative lambda. Okay, this is the so-called eigenvalue equation. From this, we get two ODEs. I'm going to write these down here like I've been doing. So we get Laplace, let me get my pen back. So we get the Laplacian of f equals negative lambda f. And we have these four boundary conditions up here on f. We have f of 0 y equals f of pi y equals f of x0 equals f of x pi equals 0. Does that look familiar? This is example 1 from the previous lecture. This is the Helmholtz equation with the Dirichlet boundary conditions. We just solved this. So if you haven't watched that lecture, please do it. So next, we get the same old equation in G. So we get G prime equals negative c squared lambda g. So we know how to solve this first equation. Let me do it up here because just in case we run out of room. So we know that lambda is equal to m squared plus n squared. So I'm going to call this lambda mn. That's the eigenvalue of this equation, or this operator. It's the lambda that works. And the eigenfunction is fmn of x and y equals sine of mx sine of ny. Again, we did that in the previous lecture. Now we can plug lambda back in for lambda here, and we can write g prime equals negative c squared m squared plus n squared times g. And this is just exponential decay. It's the same thing as we saw before, just instead of an n squared here, now we have an m squared plus n squared. So, similarly, we go up here and we get that g mn of t equals e to the negative c squared m squared plus n squared t. So this is what we get for our functions f and g up here. So we were looking for a solution of the form f times g. And we said if there is one, then, well, there is one for every pair m and n that are positive integers, and they are of this form. Okay, so that means for each m and n are natural numbers, whole numbers, whole positive integers, we have a solution u of mn of x, y, t equals fmn of x, y times gmn of t. And in the interest of clarity, I'm not going to just copy these down. They're right up here. But we have one of these for each pair m and n. So our general solution is of the form u of x, y, t. This is the infinite sum over all m and n, at least 1, up to infinity. You don't have to write the infinity up there if you don't want to. So by superposition or linearity, we can add these things together arbitrarily. Bmn times f. Now I'm just going to write down, well, how about if I write down umn of x, y, t, and that's just m and n. Again, you can write this as a double sum if you want to. I just like this because it's a little more compact notation. So bmn times sine of mx times sine of ny times e to the minus c squared m squared plus n squared times t. This is our general solution. This represents the general solution to the boundary value problem. We have not touched the initial condition yet. So this describes every possible solution to the heat equation where the boundary is fixed at 0. For every initial condition, we get a different collection of coefficients. Okay, let's plug in t equals 0. So let's plug in t equals 0 and use the initial condition. So u of x, y, 0, what happens? If you plug that in, the exponential goes to 1. This goes away. We have this sum from m and n equal at least 1 of bmn sine of mx sine of ny. So what is this thing? Sometimes this is called a 2D Fourier series. It's a sum over all pairs m and n of products of sine of mx sine of ny. And we have to set that equal to this thing, which is equal to, so this is 2 sine of x sine of 2y plus 3 sine of 4x sine of 5y. Okay, so what does that mean? If this infinite, doubly infinite sum is equal to these two terms, the only way that's possible is if like coefficients are equated. So over here, the 1, 2 coefficient, b12, is 2. So we know that b12 has to be equal to 2. On the right-hand side, we have the 4, 5 coefficient is equal to 3. So bmn, when m and n are 4 and 5, is equal to 3. So b4, 5 is equal to 3. And finally, all of the other terms over here are 0. So bmn is equal to 0 for all, let's say, otherwise. So if this function right here were not as simple as a 2D Fourier series, we would have to compute a Fourier sine series or a cosine series. And what does that mean in a two-dimensional, if we have x and y? We'll do that with the wave equation. So I specifically split this up. So the first example, we have a very simple thing that we don't have to compute the Fourier sine series of. And the next one, we will have to. And it's not as bad as it seems like it would be. Trust me. Wait and see. Okay, so now we are done. We have our particular solution, and we have one place to put it. So let's do that. Let's box off this area, and let's say the particular solution. I like to say particular solution ... You should finish the sentence because any one solution can be a particular solution. So this is the particular solution satisfying the boundary and initial conditions. Or you can say satisfying the initial conditions, because we already are coming from this where the boundary conditions are satisfied. So particular solutions, let me say, satisfying the initial condition is, let's do it in red. So u of x, y, t. What is it? So it would be wrong to write an infinite sum here because we don't need a sum. This is when you have infinitely many things. We only have two terms. We have two non-zero terms. We only need to write down the 1, 2 term and the 4, 5 term. So let's do that. So you have x, y, t. We need to write down this thing for m and n are 1 and 2 and 4 and 5. So let's do the 1, 2 term first. The coefficient b12 is equal to 2. So we get 2 times sine of m is equal to 1. So sine of x, sine of 2y. And then e to the, what's m squared plus n squared? That's 1 squared plus 2 squared. So that's 5. So e to the negative 5ct. And now let's write down the 4, 5 term. What's that? So the 4, 5 term, that's the coefficient is 3. So that's b4, 5 is 3 times sine of 4x, sine of 5y, and e to the negative, oh, I forgot my c squared up there. C squared? E to the negative, what's m squared plus n squared? So 4 squared plus 5 squared is 16 plus 25, that's 41. So e to the negative 41c squared t. So this is the final solution to this initial and boundary value problem. Notice what happens over time. So heat dissipates. So when you plug in time equals 0, these go away and you get this initial condition, which is this squiggly thing. But the limit, so this thing here goes to 0 as t goes to infinity, because these exponential terms are dampers, or they dissipate, they kill off the waves. And notice that they kill off the waves with a higher frequency faster, because e to the 5t goes to 0 a lot slower than e to the negative 41t. But these, assuming c is not microscopic, these go to 0 pretty darn quickly. So the heat dissipates. And that's going to depend on whether this is metal or plastic or what the thermal conductivity is. But so, yeah, that is the heat equation with homogeneous boundary conditions. What we will do next, I'm going to tell you before I flash up the equation, is now, in the next equation, what if we do the same thing, except the boundary conditions look like this? So it's the same three sides, but now the back boundary condition is that thing. So in other words, we are just going to bump up this. Well, the short solution is we take this thing and bump it up by that. Then the solution to that is this thing bumped up by whatever the heck this function h of x is. And we actually computed this in the previous lecture, or a couple lectures ago. And remember, it involved sums of sinches and coshes, or sines and sinches, sorry. So yeah, that's the answer to example 1b, which I haven't even showed you yet, which is the same thing, same three boundary conditions, the back one's different, and the initial condition is this thing, but we have to add plus h of x. We have to bump it up by this as well. Okay, so that's coming up next. Here's that example that I just told you about and spoiled. So solve the following initial and boundary value problem for the 2D heat equation with inhomogeneous boundary conditions. Same heat equation. Three of the boundary conditions are the same, and this fourth one is this parabola that we've been seeing throughout the class. So if these are the boundary conditions, then the steady state solution is going to be that harmonic function, basically what you get if you make a drum out of this or stick this into a bucket of soap. So let me try to draw that again. So it's going to look like something like this. So this is the steady state solution. Let me put an x here. So x goes in that direction. So this is the origin 0, 0. And a couple lectures ago, we actually computed this function. So this is, when we solved Laplace's equation, we found that this was the infinite sum from n equals 1 to infinity of 4, 1 minus negative 1 to the n. I know it's a little bit messy. Pi n cubed sinh of n pi, so that was the coefficient, times, oops, let me get that a little better, times sine of nx sinh of ny. So this steady state solution, that's what it is right there. Okay, so we are basically bumping up example 1a in the previous slide by this. So we're adding this to by bumping up the boundary, we have to add it to the initial condition as well. And then as time goes on, these sine waves are going to die out. Okay, so recall what we did in the very beginning of this lecture. U of x, y, t is the steady state solution plus the solution to the related homogeneous boundary, or to the related heat equation where there were homogeneous boundary conditions. Okay, so this is example 1a on the previous slide, and we found this in lecture, I think it was 7.1 on Laplace's equation. It's right up here. So we know that the final solution, or the particular solution to this boundary and initial value problem, is we just add them together. So I'm going to do that. I feel a little bit silly writing this twice, but it doesn't hurt. So let's take the steady state solution and write that down over here. I'm basically copying what I have above, times sine of nx times sinh of ny. So this whole thing, and now I have to add those two terms that we had in the previous slide. 2 sine of x sine of y times, 2 sine of x sine of 2y e to the minus 5c squared t plus 3 sine of 4x sine of 5y e to the minus 41c squared t. So this is our final solution. And now let's go back to what we did with 1D PDEs. Remember how I said that solving a related homogeneous equation is basically just a change of variables? Well, I claim that that's true here as well. So if we wanted to, I could let v of x, y, t be what you get if you take this solution that I just boxed above, solution to this problem, and I subtract off the steady state solution. If I do that, and then I write this equation in terms of v, so clearly vt equals c squared Laplacian of v, so this up here is c squared Laplacian of u, and then clearly these four boundary conditions are, well, along these three sides we're subtracting off 0, and along the back side we're subtracting off this. So clearly v of 0 yt is equal to v of x0 t, which is v of pi yt. These are all 0. And this last one is 0 as well, because we're subtracting off this curve in the back boundary. So we're just subtracting it off there. So v of x pi t equals 0. And v of x y0, if we plug in 0, you get the solution to u, and we subtract off the steady state solution, and what we are left with is 2 sine of x sine of 2y plus 3 sine of 4x sine of 5y. And this is exactly what we got in example 1a. So as before, solving the related homogeneous equation is basically just doing a change of variables where we subtract off the steady state solution. So finally, what the picture of this is that, kind of a crude picture, a little cartoon, is that the This is example 1b. This is the solution to example 1b. This is equal to the steady state solution, this, plus the solution with homogeneous boundary conditions. This is lecture 7.1, and this is example 1a. The remainder of this lecture will be focused on the wave equation. Here's the setup. Consider a vibrating square membrane of length L. Maybe you don't want to think of a membrane, you can think of a trampoline that you might see in a gymnasium. So something like this. And it also doesn't have to be square. It works just as well if it's rectangular. Or as we'll see in a later lecture, we'll do this in polar coordinates when we have a vibrating drum. The edges are held fixed. So if this is a trampoline, then the edges are not moving. And u of x, y, t represents the vertical displacement at some point in position x, y at time t. Then u satisfies the following boundary and initial value problem for the wave equation. So first is the wave equation, utt equals c squared Laplacian of u. This is just physics. Now we have these four boundary conditions saying that the sides are all held fixed, and u of x, y, 0 is some initial displacement. That's a function h1 of x and y. And then the initial velocity is ut of x, y, 0 is some other function h2. So maybe the initial displacement is 0, and then the initial velocity at time 0, maybe a kid jumps on this, and so it goes down. Or maybe this is a membrane, you're pulling it down, a piece of rubber, and then you're letting go. So you have two time derivatives. You need two initial conditions. Unlike the wave equation, you had one time derivative. So think of this as one of those ball problems that you saw in calculus. Remember where you had x double prime equals negative 9.8. And then you needed, so you're dropping a ball from a roof, and you need to know, maybe here's the roof, there's the ground. You need to know two things. You need to know the initial position and the initial velocity. Are you throwing the ball upwards? Are you throwing it downwards? Or are you just letting it go? Similarly, you need the initial displacement here and the initial velocity. Think of this as the two-dimensional version of dropping a ball from the roof, or maybe better, a mass spring system, because every point here is going to be vibrating up and down, up and down, up and down. Not surprisingly, it's going to involve sine and cosine waves. And so we will solve it next. Here's what we're going to solve. The following initial and boundary value problem for the wave equation. So again, this is the wave equation. These are the four zero boundary conditions, the homogeneous ones. Our initial condition is this function. I'll say what this looks like in a moment. And the initial velocity is 0. Okay, so we have this trampoline. And now what does this look like? Well, this is a parabola in both the x direction and the y direction. So let's just say this is x and this is y. So that is going to look like, I don't know how well I can draw it. So something like that. And yeah, so it's I don't think it's technically a parabola, paraboloid. It's parabola or paraboloid-ish. Okay, let's solve this. I'm not going to go through every detail like I did before, because a lot of them are the same, but we will assume that u of x, y, t equals a function of position, f of x, y, times a function of time. So when we plug this back in, we've done this before, I'm going to skip steps. UTT is fg double prime, and this is c squared Laplacian of u. So that's equal to c squared Laplacian of f times g. So we're going to divide through by c squared fg over here and c squared fg over here. And again, the f's cancel on the left-hand side, and the c squareds and the g's cancel on the right-hand side. And what we get is g double prime over c squared g equals Laplacian of f over f, and that's equal to a constant. Let's call it negative lambda, because again, this depends only on time, and it's equal to something that depends only on position. Okay, so these four boundary conditions, as before, are going to tell us that f of x0 equals f of 0y equals f of x pi equals, well, I ran out of room here, f of pi x equals 0. So we have two ODE, or we have an ODE and a PDE. So this eigenvalue equation, let's write down what we get. So we get the exact same thing for f. And that should not surprise you, because nothing in the spatial variables has changed. The only difference is that we have an extra time derivative here. So if anything's going to change, and it'll be in the time variable. Okay, so we have f of x0 equals f of 0y equals f of x pi equals f of pi x equals 0. Same PDE. This is a Helmholtz equation with Dirichlet conditions. And now for g, we have g double prime equals negative lambda squared c squared lambda times g. Okay, so several things. First of all, we know that lambda is going to be equal to, for every m and every n, there's a lambda which is m squared plus n squared, and fmn of xy equals, the eigenfunctions are sine of nx, mx, sine of, doesn't matter, sine of ny. Okay, now for g. First of all, we can plug this back in and write this as negative c squared m squared plus n squared times g. And one more thing. We have these zero boundary conditions. And here we actually have a zero initial condition. We don't always have that. It's possible that the initial displacement and the initial velocity are non-zero. But in the event when we have one of these being zero, let's use this. This tells us that f of xy times g prime of 0 equals 0. Do you see why? Because ut equals f times g prime. Okay, so this tells us that g prime of 0 equals 0. Let me underline that with red, because I've done all my boundary conditions with red. Okay, so we also have that g prime of 0 equals 0. So this is what we have for f and g, and these are our solutions. Well, let me write down what g is. Okay, so what is g? I'll box this right now because g might take up a couple more lines. So when you look at this equation, what should be jumping out at you is sines and cosines. G double prime equals negative. Think of this as omega squared. So g of mn of t equals, now I don't like to put constants in front of these because we'll put them in front later, but I need to because I have a cosine and b sine. So I'm going to write this as a mn cosine of the square root of this thing. That's omega squared. So that's that's cosine of c times the square root of m squared plus n squared times t, plus bmn times sine of c times m squared plus n squared t. So that's g. But we have this zero initial condition here. So let's do that. Let's take the derivative and plug in 0. Now, I think we're all adults now. We don't need to, I'm not going to take the derivative of this and then plug in 0. I'll do it all at once. So let's let's do this together, talk it through. What is gmn prime of t? What happens? So you get, or of 0. That's what I meant to say, of 0. So what happens? You have, I'll do part of it. So you have amn, and then you have the constant will come out, c times the square root. I don't even need to write m squared plus n squared times, oh sure, it's not hard, times sine of, I'm just going to do, well, we have 0, so I'm just going to write sine of 0. That's easy. Oh, and doesn't matter, but we need a negative sign there. And then plus bmn times c times m squared plus n squared times cosine of 0. And this, of course, is 0, and this thing here is 1. So that means that g prime of mn of 0 equals bmn times c times m squared plus n squared equals 0. Well, c is non-zero, and m squared plus n squared is non-zero, so we conclude right away that bmn is equal to 0. So in other words, the sine term goes away. And so because of that, I don't really need to write this amn. I'm now going to write up here that gmn of t equals cosine of c times m squared plus n squared times t. If you're worried that I'm dropping this constant, don't worry, it's coming back. Okay, so there we go. Now for each m and n. Now, do these things have to be bigger than, or is 0? What happens if these are 0? Well, if m or n is 0, either one of them, then f is 0, so the whole thing is going to be 0. So let's say these are at least 1. We have a solution u mn of x, y, t, which is f mn of x, y times g mn of t. And so that's this sine of mx, sine of ny times cosine of that. So the general solution, so what's the general solution here? This is going to be u of x, y, t equals the sum for all m and n at least 1 of b m n. I don't know, do I want to call it b m n or a n n? We have a sine and cosine here, whatever. Let's call it b. And then what? So we have sine of mx times sine of ny times cosine of c m squared plus n squared t. Okay, so that is the general solution. How does this compare to the heat equation? So the heat equation, this cosine term was e to the minus c squared m squared plus n squared t for the heat equation. And why is that? So this ODE and G, instead of being sines and cosines with 2 derivatives, there was 1 derivative. It was an exponential function. That came from the fact that there's 1 time derivative here instead of 2. That's one thing to notice. And other thing to notice, what if I had switched this? So instead of my trampoline starting off with this and letting it go, initial vertical displacement being 0, what if I had started with a flat trampoline and jumped on it or punched it upwards? So suppose my initial velocity were this thing and my initial position were 0, what would have happened? Well, instead of g prime being 0, we would have had g being 0. And instead of killing off the sine term, we would have killed off the cosine term. So this cosine would have been a sine. Okay, I've run out of room, so on the next slide, I will summarize what we have done before. I will write the general solution, and then all we have to do is plug in the initial condition and figure out how to set it equal to that. Here's what we've done so far. We found the general solution to this initial and boundary value problem for the wave equation, and that's right here. I've written it here as a double sum. Okay, so now let's plug in the initial condition. So let's plug in t equals 0. Okay. U of x, y, 0, what happens? So this is unchanged. The cosine term goes to 1 because cosine of 0 is 1. So we get this. I'm going to write this as a double sum now just because that's what I did above. Again, it really doesn't matter. So this is bmn sine of mx sine of ny. Now, what is this? I claim that this thing here we can write as a product of Fourier series. So say m equals 1 up to infinity of, now what do I want to call my coefficients? How about this one? I'll do capital Bm sine of mx times n equals 1 to infinity of, let's call this beta n sine of ny. Okay, so why are these things equal? Let's just think about what this is. So what is this thing on the left-hand side? The left-hand side here is, it's going to look like this. It's going to be b11 sine of x sine of y plus b12 sine of x sine of 2y plus etc. plus b21 sine of 2x sine of y plus b22 sine of 2x sine of 2y plus etc. And in the end, we're going to get a bmn sine of mx sine of ny for every single pair m and n. That's what this is. It's this doubly infinite sum. What is this thing on the right here? This thing on the right is equal to, well, for every m and every n, there's going to be in this case, a b1 beta 1 sine of x sine of y plus b1 beta 2 sine of x sine of 2y plus dot dot dot. See where I'm going with this? b2 beta 1 sine of 2x sine of y plus b2 beta 2 sine of 2x sine of 2y. It's exactly the same thing. For every m and every n, we're going to have a sine of mx sine of ny term, which is the coefficient here is going to be capital B m beta n. So this is just two different ways to write. This double Fourier series thing is really just a product of two Fourier series. And this thing here, I have to set this equal to x times pi minus x times y times pi minus y. So how do I write these? So I have to write this both of these in a Fourier series. So I have to set these things equal and these things equal. And we know how to do that. We know that in this case, Bm is equal to 4 times 1 minus negative 1 to the m over pi m cubed. And we know that beta n is equal to 4 times 1 minus negative 1 to the n over, oops, I put my parentheses in the wrong place. Oh no, that's right. I had it right originally. Over pi n cubed. So and hey, look, we know that BMN, I mean, this B11 term is equal to B1 beta 1. This B21 is equal to B2 beta 2. The coefficients have to be the same. So we know that beta MN is equal to this product right there. So let's write that down here. I don't know what else I need to say about this. We know that BMN is equal. So what do we have to do? To use the initial condition, all we have to do is figure out what BMN is. And we just did that. It's this times that. That is all. So BMN is equal to, well, let's multiply these together and see how it simplifies. So we get a 16 on top. We get a 1 minus negative 1 to the n. We get a 1, or m, and a 1 minus negative 1 to the n. And then on the bottom, we get a pi and a pi, so we get pi squared, m squared, or m cubed, n cubed. And notice that this is going to be 0 if either one of these two terms are 0. So if m is even or n is even, then, wait, even or odd? So hold on. So this is going to be 0 when? This is going to be 0 if that is 0 or that is 0. And this is going to be 0 if m is even. So if m is even or n is even, that's going to be 0. Otherwise, both of these are going to be 2. So otherwise, we get 16 times 2 times 2, which is 64, over pi squared m cubed n cubed. And this is if both m and n are odd. So that's what this looks like. If you wanted to, we could stick this. If you really wanted to, you could rewrite this double sum, stick that into here. I'm not going to do that. I think we have all the pieces here. Finally, what this looks like, let me finish with a drawing. So this, again, looks like a little trampoline or a membrane where you are starting out with this little bubble. And what's the limit of this as t goes to infinity? There is none, because this thing is going to propagate forever. It's going to bounce back and forth. So let me finish by saying that the limit of this as t goes to infinity of u of x, y, t does not exist. Okay, that is a good place to finish this lecture. What we will be doing next is everything we've done is in Cartesian coordinates. There's a lot of natural things in polar coordinates. And if we have time, cylindrical and spherical coordinates, especially spherical, that gets really messy really quickly. And the first thing to do is to rewrite Laplace's equation in polar coordinates. And it'll be harder. But we will get the Bessel functions as eigenfunctions. In spherical coordinates, we will get the Legendre polynomials as eigenfunctions. Remember those? So that's what's coming up next. It's really useful because I think a vibrating drum is probably more common than a vibrating square membrane. Okay, so that's coming up next. Stay with us.